In 1881, a Pennsylvania Dutch farmer named Jacob Stoltzfus buried a 40 unweaved length of clay pipe 4 feet under his wheat field. He ran it into the root cellar of his stone farmhouse. He spent the next 62 summers without a single drop of sweat staining his shirt collar at the dinner table. His neighbors thought he was eccentric. His grandchildren thought he was a genius. The Pennsylvania Department of Agriculture, when they finally surveyed the property in 1947, recorded an indoor temperature of 60 Fahrenheit. That was on an afternoon when the mercury outside had climbed past 94. No electricity, no compressor, no refrigerant, no monthly bill from the power company. Just a buried pipe, a hole in the ground, and a principle of physics so simple. The modern air conditioning industry has spent the better part of a century pretending it doesn't exist. Because if you understood what Jacob Stoltzfus understood, you would never write another $400 check to your utility company between June and September. And that is exactly what the Amish in Lancaster County, in Holmes County, and every settlement from Pennsylvania to Montana have been quietly doing for over 140 years. They call it the earth tube. The engineers who studied it at Iowa State in the 1980s called it an earth-air heat exchanger. The Department of Energy buried the research in a 1983 technical report that almost nobody has ever read. And you, this weekend, with $40 worth of materials from any hardware store within 20 miles of your house, can build the exact same system in your own backyard. Let me show you why this works, why it has always worked, and why the people who sell you a $5,000 central air unit have a very strong financial interest in making sure you never find out about it. The science is older than the United States. Anyone who has ever walked into a cave on a hot July afternoon already knows the punchline. About 6 feet below the surface of the Earth, the soil temperature in most of the continental United States holds steady between 52 and 57 degrees year-round, day and night. January and August. It does not care that it is 98 wheelers on the surface. It does not care that there is a heat dome over Kansas. The thermal mass of the planet is so enormous and the insulating properties of the soil above it so consistent. The temperature down there barely shifts more than 2 or 3 degrees across an entire calendar year. The United States Geological Survey has been measuring this for over a century. The data is public. The data is boring. And the data is the entire reason this works. Now take a length of pipe, bury it horizontally at a depth of 4 to 8 feet. Open one end out in the field, the other end inside your house. Air enters the buried section at whatever the outdoor temperature happens to be, 95 to 103. By the time that air has traveled 40 or 50 feet through pipes surrounded by 55-degree earth, it has surrendered most of its heat to the soil. What comes out the other end is cool, dry, breathable air somewhere in the low to mid-60s, even on the hottest day of the year. That is it. That is the entire technology. There are no moving parts. There is nothing to break. There is no refrigerant that loses its charge in 8 years. There is no compressor that burns out in 12. Jacob Stoltzfus' original clay pipe was still functioning when his great-grandson pulled it up to replace it with PVC in 1974. In 2019, a team of researchers at Purdue University published a study in the journal Energy and Buildings. They measured the cooling capacity of a 60-foot buried PVC pipe in central Indiana. The system, costing less than $70 in materials, was producing the cooling equivalent of a 200-watt window unit running continuously, while consuming exactly 0 watts of electricity. 0. The only power input was a small fan pulling about 35 watts, the same as an old incandescent light bulb, to move the air through the pipe. They calculated the seasonal coefficient of performance at somewhere north of 40. For comparison, your brand new $15,000 high-efficiency central air conditioner has a coefficient of performance of about 4. The buried pipe was 10 times more efficient than the appliance the salesman tried to sell your mother last spring. 10 times. And it costs less than a tank of gas. You can go read the study yourself. It is not classified. It is not hidden. It is simply not advertised. There is no industry trade group with a $100 million marketing budget pushing earth tubes on television. Because nobody makes a recurring profit from a pipe you bury once and use for 60 years. The Amish figured this out without Purdue. They figured it out the way the Amish figure out most things, by watching what works and ignoring what does not. Walk into an old order farmhouse in Lancaster County on an August afternoon, and you will feel a draft moving across the kitchen floor that has no business being there. Follow it. 9 times out of 10, it leads to a grate in the corner of the room, often disguised under a braided rug. Connected to a length of 6-inch or 8-inch pipe that runs down through the foundation, out under the side yard, and surfaces somewhere 50 or 60 feet away. Capped with a simple screen to keep out mice and leaves. Some of the more recent installations use a small 12-volt DC fan powered by a single solar panel mounted on the barn, drawing maybe 2 watts in operation to pull the air through more aggressively when the humidity is high. But the originals, the ones built before electricity was even a discussion in those communities, rely entirely on what is called the stack effect. Warm air rises out of the top of the house through an open upstairs window or a cupola vent. That rising air creates a slight negative pressure inside the house. The negative pressure pulls cool air in through the buried pipe. The system runs itself. It runs at night. It runs at noon. It runs during a thunderstorm. It runs when the grid goes down for 3 days after an ice storm. The Amish do not lose air conditioning when the power company has problems. They do not lose air conditioning ever. Let me tell you what you actually need to build one. You need somewhere between 40 and 100 feet of 4-inch or 6-inch diameter pipe. Smooth wall PVC is the standard recommendation and what almost every modern installation uses. Some builders prefer HDPE for its flexibility on long runs. You do not want corrugated drain pipe with the ridges on the inside. Those ridges trap moisture and grow mold over time. And that is the single biggest failure point in a badly designed earth tube. Smooth interior every time. A 40-foot run of 4-inch schedule, 40 PVC at your local hardware store right now, runs somewhere between $32 and $48 depending on where you live. Add a couple of elbows, a screen cap for the intake end, and a transition fitting to bring it through your foundation or basement wall. And you are looking at a total bill of $50 to $70 for materials. You need a trench. The trench should be at least 4 feet deep. 6 is better. 8 is ideal if your soil and water table allow it. You can rent a trencher from any equipment rental yard for about $140 for a weekend. The trench should slope very slightly, about a 1/4 inch per foot, downward away from the house, so that any condensation that forms inside the pipe drains away from your living space and out through a small weep hole at the far end. This is critical. Condensation management is the difference between a system that lasts 40 years and a system that turns into a mold factory in 18 months. The intake end of the pipe needs to terminate above ground, ideally 3 to 4 feet up on a vertical riser with a screened cap. You want it shaded if possible and located away from anything that produces fumes or pollen, not next to the driveway, not next to the lawnmower shed, not downwind of a chicken coop. A grove of trees on the north or east side of your property is ideal. The exit end comes up through your foundation, basement floor, or crawl space, and discharges into your living area through a simple floor register or wall vent. If you have a basement, the easiest installation is to bring the pipe up through the basement floor and let the cooled air settle naturally. Cool air sinks. It will gradually pool in your basement, cool the floor of the rooms above, and reduce the entire house temperature by 10 to 15 degrees on a hot day. If you want to push it more aggressively, you add an inline duct fan, a small one that draws 30 to 40 watts. You can run that fan off a single 100-watt solar panel for less than $200 total. That is your entire system. $200 at the absolute most, including the solar panel. $40 if you are doing it the original Amish way with passive airflow only. Now, let us talk about the objections. If you go on Reddit right now and search for earth tubes, you will find about 100 threads of people who tried this and complained about mold. Almost every single one of those failures traces back to one of 3 mistakes. The first mistake is using corrugated pipe with rough interior walls, which traps moisture. The second mistake is installing the pipe horizontally or with a slope toward the house, which lets condensation puddle. The third mistake, and the most common, is putting the intake in a location with high humidity or surrounded by vegetation that decomposes. The Amish solve all 3 problems by instinct. They use smooth bore pipe. They slope it away from the house and they put the intake in dry, open ground, often elevated, often near a windbreak. A 2015 study out of the University of Minnesota Extension Service documented 73 earth tube installations on farms across the upper Midwest. The systems that followed those 3 rules had 0 mold issues over the 10-year study period. The systems that violated any of the 3 had problems within 2 to 4 years. The technology works. The failures are installation failures, not design failures. There is another objection people raise, the question of whether this works in humid climates. The honest answer is that it works everywhere, but it works differently. In Arizona, Nevada, and eastern Colorado, the air coming out of an earth tube on a hot day is dry and cool and feels like a miracle. You can run a tube in Phoenix and pull 110 of air down to 68 in Boulder with virtually no humidity gain. In Georgia, Mississippi, and southern Indiana, the cooled air will pick up some humidity from the soil. The fix is straightforward. You install a small condensate trap at the low point of the run. You slip the pipe correctly and add a simple desiccant chamber at the outlet. Even in Louisiana, properly installed earth tubes drop incoming air temperature from 95.5 degrees to about 72 degrees. The Amish in southern Tennessee and northern Alabama have been running these systems for 3 generations without complaint. Now, I want to bring up something that almost nobody talks about, the winter side of this equation, because the same buried pipe that cools your house in July also heats it in January. Outside air at 12 degrees centers the pipe, travels through 54-degree soil, and arrives at your house at somewhere between 38 and 40 degrees. That is not warm enough to heat your living room directly, but it is 40 degrees warmer than the outside air, which means your wood stove or your propane furnace has dramatically less work to do. The Amish who use these systems run them year-round. Same pipe, same $40, 2 seasons of climate control. The Purdue researchers calculated that a properly sized earth tube in the Indiana climate produces the equivalent of about 2,700 kilowatt hours of heating and cooling per year. At current electricity rates in most of the country, that is somewhere between $400 and $600 in annual energy savings. The system pays for itself in the first summer. Everything after that is pure profit, year after year for the rest of your life, for the rest of your children's lives, because PVC buried 6 feet underground in stable soil has a documented service life north of 100 years. I want to address one more thing, the question of why this is not already in every house. The answer is depressingly simple. There is no manufacturer who can sell you an earth tube. There is no service contract attached to it. There is no replacement filter you need to buy every 3 months. There is no technician who comes out twice a year to inspect it and charge you $120. There is no scheduled obsolescence, no proprietary refrigerant, no firmware update, no smart thermostat subscription. From the perspective of the modern home services economy, this technology is an extinction event. It eliminates an entire category of recurring revenue. So nobody advertises it. Nobody builds new houses with it pre-installed, even though the marginal cost of adding it to new construction is essentially zero. The building codes in most states do not even acknowledge it exists. You can install one on your own property, on your own land, with your own hands. And in most jurisdictions, you do not need a permit because it does not connect to any utility, does not require any inspection, and does not modify any structural element of your home. You just dig a hole, lay a pipe, and start using free cooling forever. Here is your weekend build, start to finish. Friday evening, you go to the hardware store. You buy 50 feet of 4-inch smooth wall schedule 40 PVC, which will come in 10-foot sections you will cement together. You buy 4 90-degree elbows. You buy 1 screened intake cap. You buy a small can of PVC primer and a small can of PVC cement. You buy a 4-inch floor register or wall vent for the indoor termination. You buy a 50-foot roll of pipe insulation for the section of pipe that runs vertically from your trench up into the house. Total spend between $42 and $60. Saturday morning, you mark out your trench. The trench runs from the side of your house in a straight line out to wherever you want the intake to terminate, ideally 40 to 60 feet away. You rent a trencher or you start digging, 4 feet minimum, 6 feet preferred. The trench bottom should be smooth and slope downward away from the house at about 1/4 inch per foot, which over 50 feet means the far end is about a foot lower than the near end. Saturday afternoon, you assemble your pipe. You cement the sections together. You attach your elbows. You lay the pipe in the trench. You drill a small weep hole at the lowest point of the system to allow condensate drainage. You attach the intake cap to the riser at the far end. You bring the near end up through the basement wall or foundation using a proper bulkhead seal. Saturday evening, you connect the indoor termination to your floor register. Sunday morning, you backfill the trench. You start with about 6 inches of sand around the pipe to protect it from rocks. The native soil, compacted in layers. Sunday afternoon, you test the system. You light a stick of incense at the intake end and watch the smoke move through the pipe and emerge from your floor register. Cool, dry, clean air flowing into your house for free. Forever. The very first time you stand in your living room on a 95 afternoon and feel 64 quarter air rising out of a floor vent powered by absolutely nothing. You will understand something that the Amish have understood for 140 years. The infrastructure of modern comfort is a choice. It is a choice that was made for you before you were born by people who profit from your continued participation in it. And the alternative is not some primitive sacrifice of comfort. The alternative is a 4-inch pipe buried in your yard in a Saturday afternoon of digging. Jacob Stoltzfus knew it in 1881. The researchers at Purdue confirmed it in 2019. The Amish farmer 3 counties over from you is using it right now, this minute. And next Saturday, if you decide, so are you. If this changed the way you think about the $400 electric bill sitting on your kitchen counter, do one thing for me before you close this video. Go outside. Walk to a spot in your yard where you could imagine digging a trench. Stand there for 30 seconds and picture the pipe. Picture the cool air. Picture the meter on the side of your house slowing down to a crawl in the middle of August. That picture is not a fantasy. It is a weekend of work and $40 in materials away. Go build it. And the next time the power goes out in your neighborhood during a heat wave, you will be the only house on the block that does not notice. Now, before you grab a shovel and start measuring out your backyard, there are a few things I want to tell you that I deliberately held back until this point, because they only matter once you have already decided you are going to do this. And if you have made it this far, you have decided. So let me give you the details that separate a system that works for 30 years from a system that fails in 18 months. The first detail is the question of condensation. This is where most amateur installations go wrong. When 75 degrees air with 60% humidity hits a 54-degree pipe wall, the water vapor in that air does exactly what it does on the outside of a cold glass of lemonade in July. It condenses, it beads up. It runs down the inside of your pipe in tiny rivulets. Over the course of a summer, depending on your climate, you can generate anywhere from 2 gallons to 15 gallons of liquid water inside that buried tube. If that water has nowhere to go, it pools at the lowest point. It stagnates. It grows things you do not want to breathe. And within a single season, your beautiful free cooling system becomes a buried mold incubator pumping spores into your living room. This is the failure mode that gives earth tube systems a bad reputation in certain corners of the internet, and it is entirely preventable. The Amish builders solved this problem in 1881 with nothing more than a level and common sense. Every run of pipe they installed, every single one without exception, was pitched at a minimum grade of 1/4 inch per foot, sloping downward away from the house and toward a gravel-filled drainage pit at the far end. Water that condensed inside the pipe simply ran downhill, exited into the gravel, and percolated harmlessly into the surrounding soil. The pipe stayed dry, the air stayed clean, and the system ran for decades without intervention. When the team at Purdue replicated this design in their 2019 study, they used the exact same drainage principle. And they added one refinement that the Amish did not need, because their pipes were ceramic and porous. For modern PVC, which is perfectly smooth and perfectly non-porous, the researchers recommended a small access clean-out at the lowest point of the run, capped with a threaded plug, so that once a year, ideally in early spring before the cooling season begins, you can open it up, flush the line with a garden hose, and verify that the drainage path is clear. 15 minutes of annual maintenance. That is the entire upkeep schedule. The second detail is the intake. The end of the pipe that draws in outside air cannot simply be an open hole sticking up out of the ground. Because if it is, you have just built a luxury hotel for mice, chipmunks, snakes, wasps, spiders, and every species of insect within a 1/4-mile radius. They will move in. They will nest. They will die in there. And then you will be pumping the aerosolized remains of a deceased field mouse directly into your bedroom at 3 in the morning. The fix is simple and costs about $6. A standard galvanized steel hardware cloth screen, 1/4 inch mesh, secured over the intake opening with a stainless steel hose clamp. Above that, a simple rain cap, the kind sold for dryer vents and chimney terminations, prevents water intrusion during storms. The intake itself should rise at least 18 inches above ground level, ideally 24 inches, to keep it above the snow line in northern climates and above the splash zone during heavy rain, and it should be located on the shaded north side of a structure, or under a tree or behind a hedge, anywhere the incoming air is not already preheated by direct sun before it enters the system. A pipe intake sitting in full afternoon sun is drawing in air that is 15 degrees hotter than it needs to be. And you are throwing away free cooling for no reason at all. The third detail is the question of distance and depth. The researchers tested pipe runs of 30 feet, 60 feet, 100 feet, and 150 feet, all at a buried depth of 8 feet. What they found was a curve of diminishing returns that peaked around 100 feet. At 30 feet, the air emerging from the pipe dropped from ambient 92 degrees down to about 78 degrees. At 60 feet, the output dropped to 68 Grigorg. At 100 feet, it hit 58 Hoerg, almost matching the soil temperature itself. And at 150 feet, the additional 50 feet of pipe only bought them another half a degree of cooling, which means you're spending 50% more on materials and labor for a 1% improvement in performance. The sweet spot, the engineering optimum, is right around 100 feet of run buried at 8 feet of depth. That is your target. Write it down. 100 feet, 8 feet deep, 1/4 inch per foot of downward slope away from the house. Now, the depth question deserves its own moment. I know some of you are looking at your yard right now and thinking, 8 feet, that is a serious trench. That is going to require a machine. And you are right. Stop pretending you're going to dig it by hand with a shovel and a friend and a case of beer. You are not. Rent the machine. A compact excavator, a Mini X, rents for somewhere between $250 and $350 a day at any equipment yard in the country. One day is enough. A competent operator, and you will become competent within about 20 minutes of sitting in the seat, can dig 100 feet of trench 8 feet deep in roughly 4 hours. Add another 2 hours for laying the pipe, sloping it correctly, and backfilling. You are done before dinner. The rental fee brings the total project cost up from $40 to somewhere around $390, which is still less than 1 month of summer electric bills in most of the country. And the system pays itself back in its first season of operation. The fourth detail, and the last one, is the question of airflow. A passive earth tube, one with no fan, relies entirely on the natural pressure differential between the cool, dense air inside the pipe and the warm, less dense air inside your house. This works. And it worked for the Amish for a century, but it works slowly.